Greetings. Welcome to today's class. Just to briefly recap what we studied in the previous lecture, we just had a broad overview of scores, what we are going to learn, and then we looked at this course as consisting of 5 modules. We would first start off with a brief overview of dynamic systems, then a brief recap of rigid body dynamics. Then we will go into application of these ideas for longitudinal dynamics, lateral and vertical dynamics. Okay, so that is going to be the flow of information in this particular course. So with that in mind, we started off with this notion of dynamic systems. So we learned that, by a system, we would essentially consider an entity to which we provide an input U and we obtain an output Y. And both the input U and output Y are functions of that. Okay, so that's how we are going to visualize the system. And then ultimately the input and the output are related through this mapping S, and that relationship is what is called as a mathematical model of the system, right? And broadly we can do 3 problems. The first one is if we are given the input U and the output Y, we can find S, which essentially deals with the synthesis of the mathematical model. Once we obtain a model, we can do also analysis of the system. We can provide different inputs, and then we can essentially figure out the corresponding outputs. Then comes the problem of control, where in order to get a desired output, the question is what should be the input to be provided to the system. So that problem of control is something which we will look in the course on control of automotive systems. Okay, so in this particular course, we will be looking at the first 2 problems predominantly, the synthesis problem and the analysis problem. Okay, and then we looked at what are the mathematical tools that will be required. And as I mentioned, I would be briefly collecting main concepts from, these mathematical ideas, as we go along. Okay, so that's something which I will. So now in today's class, let's start off with our further discussion on dynamic systems. So as we have already seen, we essentially take a system as an entity S, to which we provide this input U, and we get this output Y, right? Yeah, so that is what our system is. So we are essentially going to look at different classification of these systems. Okay, so as we already know, we have Y of t to be some S of U of t. Okay, so that is what our mathematical characterization is. Okay, so let's look at some classes of systems. Okay, so the first one is what is called a linear system. So what is a linear system? Okay, so for example, let us consider some example from the automotive domain, right? Let's say steering a vehicle. Suppose I'm driving a car under some road conditions, and I am essentially looking at the problem as one where my steering angle is the input, and the orientation of the vehicle is the output, or the heading angle of the vehicle is the output. Okay, or the yaw angle of the vehicle is the output. Okay. So now, when do I call the corresponding system or the system visualization as a linear system? So let's look at this. So suppose let's consider the system is, and we provide an input U1, okay, to the system, right? And we get an output Y1 from. Okay, so I give some arbitrary input U1 and then I get an output Y1 from the system. So the same system, yes, okay. I give an input U2 and I get an output Y2, okay, from the same system. So in the context of our example, let us say I initially gave a steering wheel angle input of 10 degrees, right? And I got a heading angle change of, let's say, 2 degrees, right? And then I turned the steering wheel by 25 degrees. I got a heading angle change of, let's say, 5 degrees. Okay. Now, if I provide an input to the system, which is the sum of the two inputs, okay, U1 and U2, if the system were linear, I need two conditions to be satisfied. Okay, so what is the first condition? If I provide U1 plus U2, I should get Y1 plus U2. So initially in the problem of example that we were considering, when I provided a steering wheel angle input of 10 degrees, let's say the heading angle changed by 2 degrees, and I provided 25 degree steering angle, the heading angle changed by 5 degrees, right? Now, if I provide 10 plus 25, which is 35 degrees of steering wheel angle input, I should get 2 plus 5, which is equal to 7 degree change in the heading angle. Okay, so that is the first condition. Okay, and then the second condition is that I take any scalar multiple, okay, of an arbitrary input. Okay, let's say I have U1, and then I essentially multiply it by some scalar C, okay, some real number. What should happen is that the output also should be the same corresponding original output Y1 multiplied by the same scalar. Okay, and this should be true for all real numbers C, okay, and for all inputs U1P and okay. So in the example that we consider as far as steering is concerned, so let us say I gave 10 degrees of steering wheel angle input, I got a heading angle change of 2 degrees. Now let's say I gave 20 degrees of steering angle input. So if the system were linear, I should get 2 times 2 degrees, right? Which is 4 degrees of heading angle change. Okay, so that is this second condition. Of course, the script R means the field of real numbers. Okay, so essentially, you can have any real number. I scale the input, the output also should be the corresponding output scaled by the same real number. Okay, so then if both these conditions are satisfied, then we have what is called as a linear system. Okay, some will write both these conditions as a single condition. How will they write as a single condition? Let me write it. So they will essentially consider the following. They will consider what is called as a linear combination of any two arbitrary inputs, U1 and U2. The linear combination is C1 U1 plus C2 U2. Okay, so this is what is called, sorry, this is what is called as a linear combination of the inputs U1 and U2. All right, so that's what it is. Okay, so essentially we have a linear combination C1 U1 plus C2 U2. If the system were linear, what should happen is that the output should be C1 Y1 plus C2 Y1. Okay, so that's what I should get as the output for a linear system for all C1 belonging to the field of real numbers and all C2 belonging to the field of real numbers. Okay, so this is what we can write these two conditions as a single condition. Okay, so this is the definition of a linear system. Some people will call this as the principle of superposition. Okay, so if you heard this term, we are essentially talking about this definition of linear. Okay, so this is what is called principle of superposition. Okay, so I hope this definition of linearity is clear. So essentially what it means is that like we should have a linear system obeying these rules, right? So in a very physical sense, like if we give any two arbitrary inputs, we sum them, we should get the sum of the individual outputs. If we scale any input, we should get the same individual output scaled by the same number. Okay, so that's what linearity would imply. Okay, so that's when a system is said to be linear. So any system which or any mapping, yes, which does not satisfy this is what is called as a non-linear system. Okay, so that is how a non-linear system is defined. So if you look at real life, like most systems are going to be non-linear, but we will look at linear approximations of those non-linear systems for first cut analysis. Okay, so that is why this definition is useful. Okay, now the second classification is what is called as that of a time invariant system. So this term looks to be very counterintuitive, right? Because we are looking at dynamic systems, right? So where I mentioned that the independent variable is time, and then all variables depend on time, right? Or functions of time. So when all variables are varying with time, like what does it mean by saying time invariant, right? So you can see that the phrase time invariant is used as an adjective to the word system. Okay, so let's figure out what this means. Okay, so what this means is the following. So let us say I plot the input u of t versus time. Okay, and let's say we plot the corresponding output. Okay, and just plotting some arbitrary signals for the sake of understanding. Okay, so suppose let us say I initially give what is called as a step input. Okay, u of t. So essentially we give a step input wherein like we increase the value of the signal at time t equals 0 and keep it constant. Okay, so and let us say the corresponding output, right, be something like this. Okay, it oscillates and settles down. Okay, so now let us say I give the same input but shifted in time. Okay, by some time interval capital T, I'm giving the same input. Okay, u of t, but it's shifted in time. Okay, if the system were time invariant, what will happen is that this output also will be shifted. It will be similar in pattern. Okay, same pattern. Okay, but then like it will be shifted by the same time interval, capital T. Okay, so that is what is called as a time invariant system. So in other words, what it means is that like the response characteristics of the system do not change with time. You provide the same input today, you will get some output. You provide the same input tomorrow to the same system, you get the same output. Okay, so that is the notion of time invariance. So going back to our example of steering, right? Let us say I give 10 degrees of steering angle input, I get 2 degrees of heading angle change today. I come and drive the same car tomorrow on the same road surface, everything remains the same, right? I give a steering angle input of 10 degrees, I should get a heading angle change of 2 degrees if the system were time invariant. But of course, in real life, nothing is time invariant because think about a car, right? So let's say you keep on driving the car, right? So there is going to be some wear and tear in the various vehicle systems and also the tire, right? So although let's say 1 year down the line, right, after we have used the car, and we come and essentially give the same steering wheel angle input of 10 degrees, right? I may not get 2 degrees of heading angle change. Okay. So in real life, like most systems are time varying. Okay. But then this assumption of this time invariance is very useful. And in fact, in most dynamic systems, the first cut analysis is always done by assuming that the system can be approximated as a linear time invariant system. Okay, so that is where the abbreviation LTI makes sense. LTI stands for linear time invariant. Okay, so in fact, it's very odd, right, that if you look at in real life, most systems are non-linear, most systems are time varying, right? But then, however, when we begin our analysis, we are essentially going to consider a system as a linear time invariant system. Okay, so it is just that there are well-established tools for that, and this is a very good as approximation to begin with. Okay, so that is the justification one can give. Okay, so and then depending on the problem, if the problem is highly non-linear, we can use tools corresponding to non-linear systems to analyze them. All right, so that is time invariance. The third classification or definition is that of a causal system. Okay, so when is a system said to be causal? A causal system is one that is non-anticipated. Okay, so in essence, the output of a causal system, right, at this instant of time depends only on current and past inputs. Okay, it would not depend on what inputs may come in the future. Okay, so that is a causal system. Okay, so in other words, the response of a causal system, its response at any instant of time depends only on past and current inputs. Okay, so that is the notion of a causal system. Okay, so they are non-anticipative systems. Okay, so if you so from a broad level, as I said, when we essentially look at dynamic systems, right, which is our first module. Okay, so what we typically do, what we typically start off with, or that is that we first look at causal dynamic systems. Of course, many people make the or not. I won't say many people. At least some, make the error of writing causal as casual. Okay, so please be careful with that. Okay, it's causal. The spelling is causal. Okay, so if you swap S and U, you get casual. Okay, so we need to be careful there. So we will deal with causal dynamic systems. Okay, and then we are going to look at time invariant approximations of dynamic systems. Okay, and then we are going to look at linear approximations. Okay, and to begin with, we are going to consider SISO. Okay, single input, single output. Okay, so in fact, you will see that this is the class of systems that we will be looking at. And in fact, when we deal with even vehicle dynamics modeling, you will see that our analysis will be such that the models will correspond to the mathematical models of such systems. Okay, so that is why we are learning this theory. Okay, so I hope the connection between theory and practice will become clear as we go along. Okay, so we can observe that we are essentially going to study about a very, very small subset of dynamic systems. Okay, so one may wonder, how valid this is, right? Because when I told you that in real life, right, most systems will be non-linear, right, and most systems will be time varying, right? And question becomes, how this approximation is a reasonable one. Okay, but it so turns out that it's a useful approximation to begin with. Okay, and so it is pretty useful in practice, and that is why we are going to learn about this, and then we will see how we will apply it to vehicular applications. Okay, so I hope this is clear. All right. So any questions on what we have learned till now? We just have learned about different classes of systems, right? And we have identified what class of dynamic systems we will be studying. Any questions?
Sir, an example of causal systems?
So for example, even if you look at the steering system, right? So only when you give a steering input, right, the orientation heading is going to change, right? So, correct? The heading of the vehicle at this instant of time is going to depend on the steering inputs given uh, before, right? And at this instant of time. Okay. On the other hand, if you build a automated control system, which is going to sort of anticipate some obstacle which may come, right, and take corrective action even before a driver gives a steering input, like we go into anticipative systems. Okay. So, in fact, we will come to controllers. Okay, when we do control of automotive systems, the structure of even PID controller is non-causal because the derivative term adds anticipatory behavior to it. Okay.
So it's a kind of automated systems then? These causal systems are?
So, see, in practice, most systems are causal, right, by themselves. Okay, that is, you get an output based on what input we have given currently and in the past. But when we build some controllers to automate the system to get some desired response, right? Let's say we want to do some obstacle avoidance or collision avoidance and so on, right? The controller will become anticipated. That's what I'm saying. Okay, so it's not that the entire system will suddenly become non-causal. Okay, one block of it will become non-causal. Okay, we'll look closer at it as we proceed. Okay. Right. Any other questions? Okay. So let us also consider now that we have looked at uh, the classification of dynamic systems, some standard classifications, right? Let us also look at some standard inputs. Okay, so why are we going to look at these inputs, right? Because see, these knowing these inputs, it's very useful to study the dynamic response, quantify it, and so on, right? And even you will see that we are going to use them when we even like do vehicle dynamics analysis, testing, and so on, right? So I'm sure you will start identifying with what you may have encountered, right, in your work also. When we learn about these inputs. Okay, so let's look at various classes of inputs. Let me first start off with what is called as the unit impulse. Okay, so what is this unit impulse? Suppose, let us say I plot a diagram, right? So where I am essentially plotting input signal u, this is time. I'm essentially plotting u of t, this is time. Of course, let me also draw another plot, which I will shortly fill in. I'll explain what will happen. Let us say in the first plot, I plot the signal, right? So which is essentially 0 till this point. And then like it increases like a pulse and then like stays at a constant value and then like falls back to 0 and then like goes on. Okay. So this is my signal. All right. So this is non-zero in a narrow time interval minus epsilon by 2 to plus epsilon by 2 around 0 time, and the magnitude of the signal is 1 by epsilon. Okay, so as a result, we can immediately see that the area of the rectangular signal, right? This signal is the shape of course, it's a square, right? So the rectangular signal, not a square. Okay, so the width is epsilon, the height is 1 by epsilon. Okay, so in general, it's a rectangle. So if you see the area of this signal is going to be 1. Okay, the height times width is going to be 1. Okay, so now let's say we essentially keep on shrinking this epsilon. Okay, epsilon is a positive real number. Okay, epsilon is a positive real number, and we keep on shrinking this epsilon. Okay, so what do you think is going to happen? The signal, as the epsilon tends to 0, it will go to 0. It will remain 0 till time t equals 0, and then at time t equals 0, it's going to just shoot off, right, to infinity, and then it will instantaneously come back to 0. Then like it will stay at 0. Okay, so imagine an ideal signal like this, right? So where you, which is what you get if you shrink epsilon to 0. Okay, visualize that we are shrinking epsilon to 0. So then the width of the signal keeps on decreasing to 0, while the height, which is 1 by epsilon, will go to infinity, right? So this is what is called as a unit impulse input. Okay, so the adjective unit came in because the area of the rectangle is 1, right? Yeah. And I hope now it is clear why it is like an impulse input, right? So this is also called as the Dirac delta function, delta t, in mathematics. So this is the ideal unit impulse input. Okay. So the corresponding output, when you provide the impulse input to a system, the corresponding output is what is called as the impulse response of the system. All right. So let us say we have a vehicle and then like we provide an impulse steer angle, right? Then whatever output we get is what is called the impulse response. Okay. So in fact, in vehicle dynamics evaluation, there is a test called as a pulse steer test, right? So where the steering angle is, what to say, given an input suddenly and then it is brought back to the center position, right? So the idea is essentially to generate as close to as an impulse as. So why is this test useful? Okay, we will learn more. Why is the signal useful, right? Why is this input useful? We will learn further as we go along. Okay, so what is the use of this impulse test? Of course, see, one should also realize that it's very difficult to generate an ideal impulse in practice, right? I'm sure all of us would have realized it, right? So, so imagine, having a practical system where we generate an infinite magnitude signal for 0 time, right? That's not going to be possible, right? In real life, it's going to be, something which is like a narrow band, high amplitude signal, right? So narrow time band, high amplitude, right? So if you look at reality, like even if you want to do this pulse steer test, what's going to happen is that the steering angle input is going to be something like this, right? So it's going to be a pretty what to say, it's going to increase suddenly and then like it will come back to 0. Of course, we would want to reduce the width of the signal as much as possible and increase its height, okay, to the best possible extent. Okay, so that is the impulse input and impulse response. Then the second input which is useful in system characterization is what is called as a unit step input. So what is this unit step input? As we would have really readily understood from the English words, right? So what we have is that like if we plot u of t versus t, what's going to happen is the following, right? So we are going to have till time t equals 0, the input is 0. And then at time, after time t equals 0, the input just increases, goes to 1 and stays there. Okay, so that is why it's called as a step input. Okay, so it's in the form of a step and the magnitude of the step is 1. Okay, so this is what is called as a unit step input. Okay, so the corresponding output is what is called as a step response. Okay, so when we provide the unit step input to a system, the corresponding output is what is called as a step response. Okay, then there is what is called as a unit ramp input. So I'm sure by now we would get a feel of what this signals, right? So all of us know what a ramp is. So what is a unit ramp? Let's plot it. Okay, so a unit ramp is going to have a slope of, okay, so essentially I plot a ramp, okay, and its slope is 1. Okay, so that's what it is. Okay. So why are we doing all these things? I will explain to you shortly. And the corresponding output is what is called as the ramp response. All right. Okay. So that is the unit ramp input and the ramp response. Okay, and then like we can also have sinusoidal. Okay, so sinusoidal inputs, are of the form sine omega t cos omega t. So u of t is of the form sine omega t cos omega t, and we essentially provide these inputs, and then the output that we get is what is called as frequency response. Okay? Because frequency is the main signal, which the main parameter, right, which characterizes this signal, the sinusoidal signal. So essentially, we get what is called as the frequency. Of course, we need to be a bit careful here. Please note that when we write sine omega t and cos omega t, omega is the angular frequency. Okay, so its unit in the SI system is radians per second. And but in practice, we talk about frequency in hertz, right? So you need to multiply frequency in hertz by 2 pi, right, to convert it into angular frequency in radians per second. Okay, so just thought I would share that with you because we need to be careful, right, when we essentially do this conversion. Okay, so these are the typical inputs that we have: the impulse, the step, the ramp, and the sinusoids. Why are we considering these four inputs? And we will see that, by and large, even in vehicle dynamics testing, we'll have pulse steer, step steer, right? And, sign steer and so on, right? Where many of these standard handling tests will give these inputs, right? So why these inputs, right? So it so happens that, many times we make this assumption of linearity, right? And as we just saw, when we have a linear system, right, we can have the superposition principle to hold, right? So you give any arbitrary inputs, you find the corresponding individual outputs. You give now a new input, which is a linear combination of these arbitrary inputs. The corresponding output can be easily found, right, as the same linear combination of what to say, the individual outputs, right? So consequently, what happens is the following, right? So we study the response of the system, right, to these individual inputs, and it so happens that in practice, right, most inputs can be written as some arbitrary linear combinations of these inputs, right? The impulse, the step, ramp, and so if we know what is the output to the individual inputs, we can always figure out the output to any arbitrary input. Okay, so that is point number one. And second point is that we also get a lot of insight into the system's response and behavior by studying the response of the system to these inputs. Okay, and that helps us in having some quantification of system performance. Okay, so that is also something which is quite useful to us. Okay, so those are the reasons why we are essentially going to consider, right, and look at these classes of inputs, okay, as standard inputs. Okay, so I hope that point is clear. Any questions? Okay. So let me now do an example to just show you how we get this model and then how we interpret things, right? So let us say we consider a simple 1 degree of freedom mass spring damper system, right? So which all of us are familiar with. Okay, DOF stands for degree of freedom, right? So we will define degree of freedom later on when we revise dynamics. Okay, so let's consider this 1 degree of freedom mass spring damper system, right? So all of us are familiar with it. Let me draw a schematic to just explain it, and then we'll write down the equation. Okay, so let us say I consider a lumped mass m, okay, which is resting on a surface. Okay, this is mass m. Okay, so I essentially model the system compliance by using a spring with a spring constant of k, and then I model the system damping. Okay, viscous damping using a viscous damper with a damping coefficient of c. Okay, and let's assume that I'm giving a force f of t of this mass, and let's use displacement from its initial equilibrium state Px. Okay, so this is our mass spring damper system. So now, in fact, if I visualize this as our system, right, in our standard visualization of a dynamic system, so what happens to this mass spring damper system? Okay, so the mass spring damper dynamic system, I can essentially visualize it as a system to which I give uh, f of t as the input, right? So the force is the input. And then like what we have is that like we have the displacement as output. Okay, so we could visualize it in this manner, right? So I'm giving a force f of t to the mass, and then like we are getting a displacement x. So if I have to write down the equation of motion using Newton's second law, let me draw the free body diagram, this mass, m. So I have this force f of t, okay, which is applied in this direction. Then the one of the restoring forces come from the spring, okay, that is going to be kxt, and the force from the damper is going to be cx dot. Okay, so that is going to resist its motion, right? So these are the forces that come in the free body diagram. Please note, I'm going to use this notation. If I put a dot over a variable, that means that I'm indicating one derivative with respect to it. Okay, so x dot means dx dt. X double dot t means it's going to be the second derivative of x. Okay, d squared x, x of t, dt squared. Okay, so that is a notation we will follow. Okay, so essentially, having drawn the free body diagram, we can readily write down the equation of motion. Okay, so the equation of motion for the mass spring damper system can be written in this form. Okay, can be written as the following: mx double dot t is equal to F equal to ma, right? So that's the mathematical statement of Newton's second law of motion. So the net force is going to be F of t minus kxt minus cx. Why am I putting the minus sign? Because you can see that the forces are in the opposite direction, right, to that of F. So the net force is going to be F of t minus kxt minus cx of t. So now if I rearrange these terms, mx double dot t is ma, right? That's the inertia term. So if I rearrange, I'm going to get mx double dot t plus cx dot t plus k times x of t is equal to f of t. Okay, so this is the well-known equation of motion for this mass spring damper system, right? So we can observe that for this 1 degree of freedom system, we get a second order linear ordinary differential equation as our mathematical. Okay, so this is the mathematical model of the system. Okay, and this mathematical model has come in the form of an linear ordinary differential equation. Okay, so now I hope you get a feel of why we need to know about ODEs and so on, right? So this is a second order because we have till x double dot, and this is a linear differential equation. It's linear in the input f and output x, and it's what is called as an inhomogeneous ODE because there is a forcing term f of t on the right hand side. Okay, so this is a second order linear inhomogeneous ordinary differential equation. Okay, so that's what it is. Okay, we can immediately note that this is corresponding to a linear system because it is linear in the input f of t, the output x of t, and its derivatives. All right. So that is why it is linear. So I'm just correlating the mathematics and the physics. Okay, it is a linear system because we are essentially having the equation to be linear in the input f of t, the output x of t, and its derivatives. Okay, why? How do we interpret that it corresponds to a time invariant system? It is time invariant provided the system parameters mck, okay, which are the system parameters, okay, or constant. Okay, so if mck or constants, the system becomes time invariant. Okay, but if any of these parameters are time depend on time, it becomes time variant. Okay, and it is causal because the highest derivative of the output is 2, whereas the highest derivative of the input is 0. Okay, so that's why it's causal. But we will go deeper into this maybe in the upcoming classes. Okay, so right now, we can see that, like unless otherwise I apply a force on the mass, it's not going to be displaced, right? So that is why the output of the system is going to depend only on past and current inputs. Okay, so that's why it is causal. Okay, so this is an example of a linear time invariant system, right? So now, like, let me also write down some variants of. Okay, so for example, let us say I consider another example, right? Wherein I have the same mass spring damper system, but now let us say the damper and the spring have time varying characteristics. So what do we mean by this? So the damping coefficient C and the spring constant, K, are functions of time. Can happen in practice, right? Sometimes we may willingly do it. Sometimes, it may happen due to wear and tear, due to changes in the system's operating conditions, right? So if this happens, we are now dealing with a linear system, but now it is time varying, right? Why? Because the system parameters C and K are functions of time. Okay, so this is what is called as a linear time varying system. Okay, the abbreviation is LTV. Okay, so that is, I hope it is clear why it is called time varying, right? See, for example, let's say, like in a certain class of what are called semi-active suspensions, right? We may use a magnetorheological damper or a variable orifice damper and so on, right? To adjust the damping coefficients of the shock absorber, right? So then in that case, C becomes a function of time, right? So we are essentially dealing with a time varying system. Okay, so I hope it is clear how this example is related to physics. Okay, we could also have a case wherein we can have a non-linear system, right? So because in fact, if you look at most springs in practice, in fact, if you go and test a spring, right? Let's say we have a coil spring, right, which is used in most automotive suspensions, for example, right? So let us say I go and test a coil spring on a universal testing machine, right? And I essentially test it over a wide range of displacements. You will see that typically the curve will be non-linear. Okay, so we are going to get a non-linear curve. What we typically do is that, like, see, we may put the spring in a pre-compressed state, and our region of operation may be a very, very small region of operation around this initial state, right? So then what we do is that, like, we linearize about this operating state, and then, like, we take the slope of the curve as our spring constant K, okay, and use a linear spring model, right? Yeah, where the restoring force of the spring is K times X. However, consider a case where my spring is going to be compressed and expanded in this range of displacement. Okay, may happen, right, in some application. But then if you look at this in bigger range of operation, we can immediately see that I can no longer fit a linear curve, right? So because I will get a huge error, right, if I try to fit a linear curve there. So then I need to write a non-linear model for the spring and then work with it. So consequently, let us say in this wider range, I may need to write down the equation of motion, assuming a linear damper in this way, right? So I may have to write it as some K times X of t whole square. Okay, let's say the spring becomes non-linear. Okay, so consequently, due to this physical attribute, the system has become non-linear, and so has the ODE. Okay, so this has become a non-linear ordinary differential equation. Of course, one could linearize it provided the X is in a very small region, and then, like, we can get a linearized model. Okay, so that is possible. We will learn some related techniques or examples as we go along. Okay, how we linearize and get linearized models. Okay. So these are a few examples, right? So what we have done is that like we have just taken this basic mass spring damper system, and then like we have written down the fundamental equation for the linear time unit system, and I have shown you when we can have a linear time varying system and when we can also have a non-linear system. Okay. So now I'm going to leave you with a question. Okay. So we have considered a simple system. We have written a mathematical model relating the input and the output. The question is, how does one solve? See, what we have done is the problem of synthesis, right? But then if we get the model, we have to put it to some use, right? We need to do analysis, right? So in order to do analysis, we need to solve the equation, right? So the question is, so how does one solve all these ordinary differential equations, right? To analyze the system. Okay, so that is something which I will briefly recap in the next class. But before coming, please do recap some tools from basic ordinary differential equations that we would have learned in engineering mathematics and also solutions to them. Okay, by the time you come to the next class. All right. Okay. So I'll stop here. Are there any questions? Okay. So if there are no questions, let me stop recording. Thank you for your attention.